It's our pleasure to have our Alexander Wiegand to talk to us today. Alexander got his PhD in 2012 from University of Bielefeld in Germany, and he did as a tracer for cosmic structures. And he is currently applied to the latest data of slow distance sky survey.
Yeah, thank you for the introduction and welcome to this perhaps rather unusual topic for this seminar, but I will try to explain a bit what I'm doing at the moment to find out how to describe the structure that we see in galaxy surveys. And basically we will do this with stuff like that, so some kind of soap bubbles that we will put around these galaxies, but I will explain you later why this is and what we try to learn from that. So first, as a short outline, I will begin with some general remarks on the analysis of structure with galaxy surveys, which has seen some quite tremendous progress over the last years, with ever bigger surveys and more data coming in. And then I will introduce these Minkowski functionals that I'm using at the moment to try to describe the structure. And then I will tell you about the data that we have been using in this project and, of course, the results that come out of that. So as I said, over the, last decade, we have seen some tremendous progress in cosmology, starting with, there has been progress all the time, but the discovery that the universe is accelerating in its expansion was quite astonishing in the late 90s of the previous century. So what you see here is the results of this famous supernovae observation that led to the discovery that omega lambda can't be zero, as would have been naturally the case when you think of the universe as being just normal matter or normal and dark matter. And in what was following, there have been various probes that are confirming this observation, and most of these probes use in some case, in some way, the cosmic structure that you see in the universe to derive constraints on these basic cosmic parameters, the matter content of the universe and the amount of dark energy that you see in the universe. And for example, the structure in the early universe is seen by the cosmic microwave background, and the structure in the more recent universe as probed by clusters or baryon acoustic oscillations. And so we have some nice consistent picture at the moment where the error bars have shrunk tremendously, and so we have some kind of concordance model of cosmology where we think that we basically know now what the underlying model is, and we know to a good extent the parameters, and the aim is to determine these parameters even better and to understand more about what this dark energy basically is. Is it just a cosmological constant, as in the simplest model you could assume, and which fits the data until now quite well, or is there more to the universe than that? So as I said, the the amount of data has increased quite a lot over the last 10 years. So in the early 2000s, there was this 2-degree field galaxy redshift survey by an Australian team that had something like 200,000 galaxies up to a redshift of 0.2. What I'm analyzing at the moment is this SDSS-3 data, which is 1.5 million galaxies in total, up to a redshift of, well, a limiting redshift of 0.8. And so we had this is factor of nearly an order of magnitude in between, and then there will be another big improvement by upcoming surveys like DESI and Euclid that in the end will provide us with 50 million redshifts, spectroscopic redshifts, and 2 billion photometric redshifts. So so there's excellent data that we can use to improve our understanding of what's going on in the universe, and the problem is then how do you test this kind of, well, of your ideas about the universe. I mean, one way is to try to push the theory to model the observables that you want to extract from your data. But at some point, for the late universe, where things are nonlinear and the easy theory becomes no longer applicable, you are faced with the situation that you have lots of data because you have lots of galaxies measured, and then you want to compare this to theory. And one way to do this is to pack all the theory that you have in the simulation and see if you can reproduce what you see in the sky, basically. So when you and then you end up with some plots like that. So you have observed galaxy positions up here from the CFA survey and the Sloan Digital Sky Survey, and the 2D FGRS. And you want to see, do you understand the theory well enough that you can produce structures that look like that? And the claim is, yeah, you can. There are in these simulations you find structures that at least optically resemble the structures that you see in the sky. But of course, this is only qualitative. So you want to compare quantitatively if the structure that you see here is really statistically the same that you see over here. And of course, there are many probes and many statistical quantities that you can use for calculating that. I mean, since the 50s, people have been looking at two-point correlations of galaxy positions, and also higher order correlations have been used to calculate, to compare galaxy distributions in simulations and in data. I mean, the two-point correlation is specifically adequate for a Gaussian distribution because it contains all the information that statistically is in the galaxy density field if the field is completely Gaussian. Our universe is Gaussian in the beginning, but as I said, in the later evolution, the evolution of the universe is becoming more and more nonlinear, and the structure is then clearly non-Gaussian. And so there are other components that become important and that you can include in the analysis to see if you really understand what's happening. The problem with these higher order correlations is that they are typically very expensive to calculate. There are some fast 3-point codes for the 4-point function. It becomes more difficult, and for higher functions, it's even more difficult. So, I mean, there have been many attempts to use quantities that allow at least some information to get out of this nonlinear structure. And one of them is these Minkowski functionals that I've been working with recently. So there are quantities defined in integral geometry and in general defined for arbitrary dimension, but in 3 dimensions you can prove that there are only 4 functionals that satisfy these mathematical requirements for these geometrical quantities. And in 4 dimensions, in 3 dimensions, you can basically trace them down to the volume of some extended configuration in space, the surface area of some extended body, its integrated mean curvature, and the Euler characteristic of this. So, as I said, the aim that we want to study here is the properties of a point distribution in general, or in particular here the galaxy distribution. And so to apply these quantities, you first have to find a way to transform this point distribution into an extended body, because otherwise the volume is 0 and the surface of points is 0, and so this would be rather trivial. So what we are doing here is we surround every point, every galaxy by such soap bubbles, and then we increase the radius of these bubbles, and as they begin to intersect, things become non-trivial, and at some point they fill out the full survey geometry, and then by increasing the radius you won't learn anymore. So the study, the quantity that we're studying is basically these 4 quantities as a function of the radius of this, of the common radius of these balls. And the interesting outcome of the theoretical calculation is then that these quantities depend on the properties of the correlations. So they include all the higher correlations in some integrated manner, and so they can probe this information that you can't access with the standard 2- and 3-point analysis. So to see how this is connected, a short slide, which is a bit formula heavy. I apologize for that, but just to give you an idea how they are connected to these correlation properties, we have for example, this V0 is the volume fraction, so the volume enclosed in these bubbles divided by the full survey volume. And it's related to, in a quite easy way, to this V bar quantity, which includes the full hierarchy of the correlation functions in an integrated manner here. So because it's an integrated way, it's much easier to measure these quantities than calculating the full correlation function. You won't have the full information, but you at least get some handle on the information that is enclosed in this structure beyond the 2-point function. If you don't have correlations, if you just have Poisson distributed point distribution, all these integrals disappear and the sum disappears, and so all you are left with is a quite simple relation for the volume fraction of a Poisson distribution, which is then only dependent on, in a simple way, dependent on the radius of these balls. So we have 2 dependencies here. One is the radial dependence through the size of the balls in this weight function here, that is in these integrals, and we have a dependence on the density of the sample, that governs the evolution as well. So what data are we applying this to? We are applying this to the spectroscopic redshifts that are measured by the Sloan Digital Sky Survey. here in the data release 12. So we have a complete coverage. This is the final data release for the SDSF3 project, and we have a complete coverage of the footprint that they attempted to measure. So you use this 2.5 meter telescope, and for each target that you want to determine the redshift of, you drill a hole in the plate and you connect a fiber to the spectrograph, and then you take spectra all over the sky. And if you do this for long enough, you have this complete coverage of, if you add these two, a quarter of the sky basically. The redshift dependence, the redshift distribution of the galaxies is shown here. So the redshifts we are analyzing go from something like 4.5 to 0.6, and we are using a constant reference density because we want to study also the dimension of the density and not only the radial dependence. So here are the Minkowski functionals, the four functionals as a function of the radius of these balls. And for V0 here, as I said, it's just the volume fraction of the volume enclosed within these balls. And so in the beginning with 0 radius, of course it's 0, and then at some point it saturates. And what you see here is this dashed line is the Poisson case, so without any structure, and the first line here is the corresponding line with structure as determined from the galaxy data, and all these other lines here are different densities. So if you subsample the galaxy data of the full data with different percentages, you get a density dependence which goes down to 5% of the full sample here. And if you study this density dependence, you can plot things in this way. So here everything is normalized to the Poisson case, which is the line that is 1 above here. So every deviation from the line above here is due to structure in the galaxy distribution. And what you can then do is to calculate the 2-point function that you can easily calculate for the galaxy sample, and plot the first term in this series that I showed you, which is linear in the density here. And so every deviation from this line here is basically due to the higher order contributions in the galaxy distribution. And what you can see here is we compare this to two different sets of simulations. One using the quick particle method, and another one using a more theory-based approach. And you can see that we can clearly say that these quick particle mocks don't describe the data very well. The data points are shown here in green and purple, and the red curve here fits much better than that. And if you want to look only at the higher order correlations, you can subtract the 2-point contribution here and only look at the difference. So for these higher order correlations, apparently they are well described by these simulations that are shown here. So to convince you that we are actually including these higher order correlations, I've shown here a fit to this density dependence. And from the formula, you would expect that it's a polynomial in the densities. And if you increase the fit order from linear to 7th order here, you see that clearly if you only include the 2-point correlations in this series, you're clearly off the data by a lot. And then if you include more and more contributions of higher orders, you find that you fit the data better, and you find that you need at least coefficients up to the 7th order coefficients, so 7-point function correlation coefficients, to describe these dependencies. So the error bars are good enough to figure out these kind of dependencies. So what do we do that for? So we want to know something about these cosmic parameters, and to test how sensitive we are to these cosmic parameters. What's shown here is the comparison of two different simulations with two different values of omega matter. One is omega matter of 0.27 and one is 0.31. And as you can see, we can clearly distinguish between the two. So the statistical difference is above 5 sigma. And so if we would have, in the simulations that we compare to, if we would have omega matter value that would be wrong by more than, well, 0.01 or so, then we probably would have detected this difference. So in this way, by comparing the simulations and to the data using this method, you can basically test if your simulation makes the right assumptions. And in this case, we could confirm that the simulations that people use for testing the data basically match what you would expect. So to conclude, that's basically also what I will conclude. So as I told you, the observational possibilities are quite remarkable at the moment. So there are lots of data available and becoming available in the near future. The Minkowski function is allowed to go to analyze the data, an aspect of the data that has not yet been analyzed in great detail. And what we could confirm here is that people understand the simulation that they did for these DR12 MOCs well enough that they can basically also determine these higher order correlations that we can access with this method well. I mean, of course, the people tested it extensively against the 2-point correlations and the 3-point correlations, but also the higher orders seem to match. So this is quite encouraging that we understand something about that the model is basically capturing what we see also in the data. So thank you for your attention. And
does it take redshift dependence into account in this? So you just put the whole model at once, not just the redshift bins, for instance?
I mean the simulations that we tested it against are done at a fixed redshift. So in this sense, it does not take a redshift evolution into account because the simulations don't model the redshift dependence at this point, which is surprising that this works. But this is due to two different effects. The structure is growing in the sense that the growth function is increasing, but at the same time the bias of the galaxies that we are looking at is decreasing. So there's some coincidence that the redshift dependence is not so strong as you would expect in the first place, apparently.
So what happens when the bubbles collide? So the bubbles are getting bigger and bigger.
Exactly.
At some point the bubble collides, And then
you
the volume is less than the volume of the two
exactly
bubbles separately.
exactly,
It's just
and that's what basically
the overlap region doesn't count.
exactly
It
that.
counts only once.
Yeah, the overlap region only counts once, and this is where the correlation information comes in, because if depending on the correlation function of the underlying field, these overlaps occur more frequently or less frequently, and so exactly from this overlap. So we are looking only at the sum of the volume of the full structure. So exactly from this overlap, we have this dependence on the correlation properties.
And similarly, the area decreases.
And similar also for the area. I mean, of course, in the beginning, if you only have isolated spheres, the evolution of this thing is trivial, basically, because you just have growing volumes of the spheres. But yeah, as soon as they collide and overlap, then you have the information on this stuff.
Our second talk is given by Dr. Peter Maksym. Peter is a postdoc fellow at Center for Astrophysics. However, this is not his first time to work here. After he got his bachelor's degree in Yale, he started work here as a member of the training assistant team for 5 years. And after that, he returned to school and eventually got his PhD degree in 2012 from Southwest. And he did his first postdoc at the University of Alabama on a variety of X-ray projects. And his current research focuses on the X-ray and the optical observations of AGN interacting with their host galaxies.
It's showing up just fine. All right. Thank you all for coming to my talk. I am here to talk about my work that I've been doing with the narrow line region of AGN. That's not supposed to happen. All right. Yes. So we think of, as you can see, we have here the classic portrait of a black hole getting ready to go boating with its friends and companions. We like to think of black holes, of course, don't operate in a vacuum. Supermassive black holes can have very complicated interactions with the surrounding elements of their host galaxies, and those interactions are important to the picture of AGN feedback, which we know to be important not only to the evolution of the galaxies themselves, but also to the duty cycle of AGN growth, and AGN accretion. I don't do this work in a vacuum either. I have a number of collaborators, most of whom are in the audience, and a couple of whom have been through the CFA at various points in the past. I got my start working on resolved observations of narrow line emission from AGN, working with Bill Keel at the University of Alabama, studying extended emission line regions selected by the Galaxy Zoo, where you have at least some evidence due to far infrared deficits relative to the expected emission from an AGN that you would expect to ionize these large-scale O3 regions that these AGN have shut down at some point in the recent past. And you can use that to study the recent accretion history of the black holes. But also, one of the interesting things that we found with resolved Hubble observations of the narrow line region is kiloparsec scale, or even sub-kiloparsec scale, you can't really see it in this image, evidence for outflows where these things have recently shut down and possibly transitioned from radiative to a kinematic outflow. But you don't need to go comb through the whole Sloan Sky Survey to find things. If you want to study the impact of radiative and kinematic feedback on the AGN host galaxies, it's best to start close. The first work that led to this project, the Chandra survey for extended emission line regions, was with NGC 4151 done by Junfeng Wang. NGC 4151 is only 13 megaparsecs away. So when you look nice and close at the center, you can see in great gory detail using Hubble, the VLA, and Chandra exactly what the AGN is doing to the inner few 100 parsecs. And this is important because when you study AGN that are far away, you're limited by the number of photons you have, but also by your resolution. You're sampling a very large region, trying to model what's actually a very complicated physical system, where you may have something like this, where the ionization cone excites the narrow line emission that you see. Here the yellow is O3, the blue is X-rays, and the purple is radio. But also you get contributions from jet cloud interactions where the mechanism of excitation may at least partially be collisional rather than photoionizational. So the first step to doing a really detailed analysis of this is to survey about half a dozen objects with Chandra and with Hubble. And when you do a direct comparison of the extended X-ray emission with the narrow line arcs that you see very prominently here that seem to trace the outer edge of the radio jets, you have room for it's the bulk of the X-ray emission is consistent with photoionized gas, but by studying not just the spectroscopy of individual subregions of the extended narrowline region, but also the morphology of individual emission line species, you start to see a physical role not just for the photoionization within the X-ray cones themselves, but also, for example, in the cross-cone filtration by warm absorbers, and also a role for the impact of the radio jet itself, as it not only collides with the surrounding gas and produces collisional X-ray emission, but also between the jet lobes and the nucleus itself. This work was done by Alessandro Paggi, and it was the first paper resulting from the CHEERS survey. But there are about a half a dozen objects for which we have these deep Chandra data of relatively low redshift galaxies, all about 0.1, or 0.01 rather. And so I've been focusing mainly on NGC 3393. NGC 3393 is known for not just it's known for possibly having evidence for sub-kiloparsec supermassive black hole binary. But when you look at the extended X-ray emission, you can say to first order that the X-ray emission also traces the extended optical narrowline emission, which is something that we've consistently seen in the past through other objects like NGC 4151. So the question is, to what extent can we approximate this as a single photoionized system, and what can we say about the different substructures that occur in this system? And in order to do that, you really need Chandra's resolution. You can, of course, go better than Chandra's native pixel scale, but if you go down to 1/8 pixel and then you deconvolve it, you start to see all kinds of really, really neat features that go even beyond that gross association between the narrow line emission and the X-ray emission. The blue here is relatively low intensity, yellow is high intensity, and these S-shaped arms that are associated with the brightest optical emission wrap around these black contours, which are the radio jets and the radio core. And you see some very different phenomenology emerging from this picture, where the S-shaped arms wrap around the outside of this northeastern lobe here, but in the southwest, this radio hotspot, which is much more intense than the other lobe, also corresponds to a very bright hotspot of X-ray emission. Now that may be evidence for interaction between that radio jet and the surrounding ISM. Now, to give you just a picture of exactly why it's important to get this resolution, which we can only deconvolve it using the full broadband from 0.3 to 8 keV. But on the left, you can see Chandra rating spectroscopy by Koss et al. Using about 500 kiloseconds of Chandra grading data. And that green circle is their extraction region. From there, you can see that there are just a wide variety of physical phenomena going on here. You have an extended cloud that's sampling different regions relative to the position of these radio jets, but also you have possible evidence for an X-ray arc. And if you're willing to look a little further afield, there may be some sort of X-ray protrusion that's either a jet or photoionized material that's gas that's being photoionized by radiation that's seeping out through this barrier here. It goes to show you that you really do need Chandra's resolution in order to do that. Unfortunately, to get this signal to noise, you also need an awful lot of photons. So what can we say about it when you break it down to constituent emission lines? Again, to first order, when you look at it in Hubble narrow filters, O3H alpha and sulfur 2, and also with different X-ray emission lines, to first order, these all seem to resemble the S-shaped arms that wrap around the radio jets, also with this more extended structure that seems to trace the spiral arms of the galaxy. And when you do a direct comparison of here, red is H alpha, green is O3, and blue is the broadband deconvolved X-ray emission, you can see some very physically distinct regions. You see X-ray emission where there's hardly any line emission at all. You see some places where there's very good correspondence, and you see other regions that are dominated by the optical line emission. So what you want to do is do a direct comparison of respective emission lines. Here we have not just the radio contours in white, but also broadband deconvolved Chandra, just the very brightest parts of it, and O3 to H alpha, which should trace photoionization, sulfur 2 to H alpha, which what you want to interpret that as depends an awful lot upon what physical mechanisms you're assuming. If you're looking at supernovae, that's a pretty darn good sign that you've got shocks due to supernovae where you have these low ionization lines in what you would expect to be this red area here. However, in that case, you don't have a constant ionizing source. So an alternative and reasonable interpretation is that this is where a small fraction of the ionizing photons are leaking through either the torus or a warm absorber and producing these lower ionization states. You see all kinds of interesting structures here. What seem to be S-shaped in just line emission in the ratio maps is, in fact, an hourglass. So that's important because one of the things that's difficult to interpret about this particular object is whether or not the jets themselves are interacting with a spiral arm, or whether they're actually inflating a bubble overall. And this would seem to indicate that this symmetry would seem to indicate that that this region too has been inflated, but and not just some sort of S-shaped spiral pattern. The different regions are all very complementary. We see possible evidence for shocks with the interaction of this radio jet and the surrounding cavity. But it's very difficult to interpret from just these two optical lines because of the ambiguity as to where the sulfur-2 arises from. These outer clouds are very highly ionized, probably at least in part because they're lower density material further out. So one of the other interesting things that you get is when you combine this with spectroscopic data, in this case, the rotational curves that have been analyzed by Fisher et al. In trying to analyze the kinematics of NGC 3393 using STIS, the actual points of the center of this emission structure doesn't seem to correspond with the kinematic center, which is a source of some confusion. But when you realize that you've got not only possible evidence for shocks and kinematic interaction in the optical and X-ray, but these very extreme hundreds of kilometers per second structures in the spectroscopy, you can interpret this region here as contributing to some sort of P Cygni structure, where the jet itself is largely projected in the plane of the galaxy. You have a very large full-width half maximum here that seems to indicate very high velocity material. It's just that it's all in the plane of the sky, and you don't see it very well. You don't see the other kinematics of the galaxy very well. It's relatively flat because this whole thing is in the plane of the sky. But when the jet actually hits a denser material, it ablates and spreads out towards us and creates this P Cygni profile. This red region is seemingly kinematically separate from the outer parts of this hourglass-shaped nebula, and probably represents the motion of the spiral arms. You can also try and do things like generate BPT diagrams, or look at the O3 to sulfur-2 ratios as a function of H alpha. And here I've broken it down into different subregions where, just for color coding, red is this cross cone where you see a very large sulfur-2 to H alpha ratio. And cyan here is the brightest H alpha regions, including the nucleus. You have the bubbles that are surrounded by that low ionization cocoon that we saw previously. And then you have different regions of the ionization cone going from northeast to southwest. These are plots that I'm still working on because there's just a lot of material here. But one thing that you can see is that in the BPT diagram, these very bright H alpha regions, and much of the ionization cone is very solidly in the Seifert part of the BPT diagram. But the cross cone region, in particular, has the locus of its points off in the liner region of the BPT diagram, which again is probably indicative of some combination of shocks from the expanding bubbles and from photoionization being filtered by intervening material. The same cross cone region is pretty systematically lower ionization than not only the bright H alpha regions, but also the bubbles and the cone as you go further out. Though I will note that this is a very noisy region, and it's very hard to pick exactly which areas to include in your diagram because you have areas that are bright in O3 and little else. You have areas that are bright in sulfur 2 and little else. And so these outer cones, at very least, you can see that they do tend to have an awful lot of their population in this very high ionization region, like you would expect for lower density material further out. All right, so what can we say about these narrow line emission structures, for which these are you can see individual photons here. So statistically, you are very, very limited by the length of the observations that you have or collecting area, for which I can say that the X-ray surveyor would be just a fantastic project, a fantastic contributor to this sort of research because you get the best of both worlds, and it's what you really need in order to bring out these emission line structures. You can try and look at them radially, bin them so that you're looking at them as a function of distance from the center. Here we have individual emission profiles from 07, neon 9, and 08 in black, with radio in brown, all offset so that you can see them more clearly. And to first order, you can see that there are these relatively low significant bumps associated with the northeast jet just on the outskirts that are the neon 9 and the 08 in particular are seem to be associated with the interface of the jet with the surrounding ISM. But the 07 emission seems to be more extended and indeed is more durable as you go out to larger radii, where you have large bins and large stretches in this binning structure where there's just no significant emission. But here in this southwestern radio hotspot, you have a very strong dip in the 08 that seems to indicate that at least this part of the 08 structure is very strongly associated with the jet hotspot and the jet ISM interaction. You do see in these ratio maps of 07 to neon 9 and 08 to neon 9 some additional evidence for that, but the most prominent features in the ratio maps are only about 2 sigma. So we would really, really like more Chandra data in order to see if we can bring those out. When you look at azimuthal profiles, you also see some very interesting trends here. The 07 is more or less straight across along the same line as the optical emission, which is what you expect when the emission from that line is associated with the same emission that the optical gas produces. But the 08 is much more strongly associated with the line of the radio jet. Neon 9 is also associated with the line of the radio jet, but again, seems to trace more the outskirts of the jet lobes themselves. And here, just to guide your eye, I've traced these different lines on the azimuthal profile, where you start at 0 degrees is right and move counterclockwise. So you have a very well-defined edge to your ionization cones in 07, and you have a very narrow core in 08. But it's, again, somewhat difficult to trace out finer structure because you do have these maybe 2 sigma features that are associated possibly with things like the transition between the jet and the surrounding ISM. So to summarize, CHEERS is the ultimate AGN survey because when we really get enough Chandra photons, we can start to resolve AGN interaction with the surrounding ISM down to scales of about 50 parsecs, which is the limit of the the Chandra mirror. The Chandra mirror is when you get sufficient signal to noise to use ACES at that level. And so the actual structures that we see associated with NGC 3393, which is the galaxy that I've been most focused on, include a low ionization cocoon surrounding it, but also complementary photoionization cones and evidence for hotspots where the jet is interacting with the surrounding ISM, over dense ISM, and either causing it to conform to the jet, or at least in the case of the southwestern jet lobe, it seems to be expanding and inflating at very high velocities. The preliminary findings that we have for the extended emission line structure seems to be consistent with previous work that Junfeng Wang and Alessandro Paggi have done with NGC 4151 and Markarian 573. In particular, that the Neon 9, we have at least hints that the emission from that line is probably associated with the jet ISM interface. But again, in order to really say some of these things with high confidence, we need deeper Chandra observations in order to not only confirm these lower significance emission line structures, but also hopefully to allow deconvolution not just of the entire broadband, but at the actual narrow bands of the emission lines, where we can say that these structures are real on the scales that we are claiming. Yes.
The thing I'd really like to see in one of these pictures is what the ALMA data would look like.
Yes. Yes, that would be fantastic. I thoroughly agree. Other things that we'd also like to see, it would be very nice to get some deeper radio data at slightly lower energies, because when you have these radio jets, at least partially filling this northeastern cavity, but you see nothing here, and yet you know all of these optical emission line structures seem to point to some sort of interaction there. So why don't we see anything radio? Is it just not deep enough? Are the electrons losing energy and therefore shifting out of band? Or maybe the jet's precessing, and that's why these S-shaped arms are the way that they are, and it's just plowing interstellar material before it. That's kind of speculative, and it would disagree with what I've heard from Travis Fisher's ongoing analysis of near-infrared IFU data that seems to suggest that this could be associated with spiral structure. But you know, if this is a symmetrical opposite side to the low ionization bubble, then that spiral structure can't be the whole story.
Can you elaborate on your deconvolution technique? Especially, you said you need a lot of statistics. What kind of concepts?
We are using the EMC2 code, which Margarita Kurovska is the expert on that. It's nice because it maintains the fainter extended structure on smaller scales that Richardson-Lucy doesn't. And as far as counting statistics, I would say that in the broadband of the northeastern cone structure, there are a bit more than 2,000 counts there from 0.3 to 8 keV. The whole structure has something on the order of 5,000 or 6,000. Only about 10% of the photons actually come from the 4 pixels in the nucleus. This is a Compton-thick AGN, so you actually have relatively little contribution from the nucleus until you start getting to above 4K eV.
Any other questions for Peter? If not, let's thank all our speakers.
You should like donate like a pizza.
Yeah, 1/8
There was one